Hi, this video is going to be about quantitative genetics, breeding and selection. And here's a problem. In a population of flies, the mean bristle number was 6.4. 3 pairs of flies were used as parents and the mean bristle number was 7.2. The offspring had a mean bristle number of 7.0. What was the realized heritability? And if you know how to solve this problem, as usual, I recommend you to stop video here, try to solve this problem on your own, and when you would be ready, you can run video again and you can compare your answer with my answer and explanation. And before I will show you how to solve this problem, this is really very easy and maybe can take less than 1 minute. I still want to show you some theory and give you terminology so you can use it later. And imagine that we have such graphic like this one, and this is would be some trait, for example, that we can measure. And because in quantitative genetics we always work with traits that can be measured. And for example, this can be tallness of anything, people or plants. And of course, here we would have some phenotype, for example, people who is going to be very small, majority would be of the average size, and here would be the tallest, and we would have them very few. So here would be frequency, and as you see, most of the people would be of the average size. And here would be our mean of population, and we call this mean of original population. And for example, if we now switch to the apples, if you want to do breeding, selection, and want, for example, to make apples that would be bigger than original population, of course you're going to choose your apples by the size. So this is going to be somewhere here on this shoulder. You would select among the biggest apples, and here would be a new mean of the selected parents. So this is going to be somewhere over here, and this is going to be mean of selected parents. And if you think that in next generation we would see picture something like this, and if you think that our bell shape would look like this, that would be too easy. And probably by now, after 10,000 years of breeding and selection, we would have apples the size of the watermelons. So this is not something that happens in real life, and in real life the new mean of the following generation, F1 generation, would be over here, between mean of the original population and the mean of the selected parents. And why this happens, why it is usually between these two means, because, and here I want to remind you formula for the phenotypic variance. Here is the formula. So variance total phenotypic equal to variance total genetic plus variance total due to environment. And of course selected parents probably would have better genetics than parents here on this shoulder of our graphic, but also their phenotype would be sum of the genetic variance and environmental variance. So genetic variance can be inherited and environment cannot be inherited. So probably these parents here just were lucky to be not only superior genetic than these parents here, or this can be plants, whatever, but also due to probably good environmental conditions that cannot be inherited. That's why in the following generation, F1 generation, there would be regression to the original mean of population, and new graphics would look like this. So the mean of population would look like this. So this like one step or two step forward and one step back, and we call this new mean response to selection. So R stands for the response to selection. And now when we know all the terminology, we can solve our problem. And here is a formula that we are going to use in order to solve our problem. So realized heritability, for example, this can be RH, would equal to mean of the original population. So this would be MO minus mean of response to selection, MR, divided by mean original mean of the original population minus mean of selected parents. And this is going to be our formula that we are going to use in order to solve our problem. So let's use the numbers here. So response to selection would equal to mean of original population, and it was in our example 6.4 minus mean response to selection, and this was 7.0 divided by mean of original population 6.4 minus mean of selected parents, and in our example that was 7.2, so 7.2. So here on the top we have minus 6 divided by minus 8, and the answer is 0.75. And as you see, this is answer A. And if you are still confused what is the realized heritability, that we find to be 0.75, or we also can say that this is 75%. Here's one more explanation. So imagine that this fragment here, I use red color, so this is fragment would be between mean of the original population and mean of the selected parents. So this fragment, if we say this is would be 100% with realized heritability, we are looking what this fragment between original mean of the original population and mean of response to selection. So if you see here, what is this proportion, or to what extent our selection would show up in the following generation. So this would be like, once again, if this fragment would be 100% and the second would be of this size. So according to our problem today, we have found that this green line is 75% of the red line. So this is realized heritability. And how I find 75%? I just multiply this number by 100, because our answer on the scale between 0 and 1, and we also can give an answer as a percentage. We just have to multiply by 100, so our answer would be on the scale between 0 and 100%. So we just can move this decimal point 2 places to the right, and this is how you convert one scale into the other scale. One more time, red fragment represent potential of selection, and green fragment represent realization of this potential in the next following generation, and we call this realized heritability. So this is all for today. Thank you for your attention. Please subscribe for more new videos that I post almost every day. Thumbs up if you like this video. Goodbye.